Now we continue the rest of the program. Moving now to salmonella. Salmonella topic with the Dr. Filip Van Immerseel. So it's my pleasure to introduce Dr. Filip. Dr. Filip is the full professor of Faculty of Veterinary Medicine in Ghent University in Belgium, and he's the head of research group focused on the host pathogen interaction. Main interest is the studying the mucosal immune response to enteric bacteria, especially Salmonella Campylobacter. So he's a prominent member of the global research community working on the foodborne zoonosis. Has plenty of publications about the zoonotic bacteria in general and about Salmonella Campylobacter in particular, and plenty again of textbooks and written books, author books, edited books about Salmonella and Clostridium. So it's a real pleasure, Dr. Filip, to introduce you, and the presentation will be about toward controlling Salmonella at farm level, how to reduce the colonization, and how to improve protection against Salmonella.
So first of all, thank you very much for the nice invitation. It's a pleasure to be here. So I'm from Ghent University. That's much better. Okay, thank you, Jeroen. So I'm from the same university as Jeroen. So we have a few departments working on animal health in general, poultry health specifically for me. So basically, I'm having a research group working on intestinal pathogens. So Salmonella is one of them. Important zoonotic pathogens. So I was asked here to give a presentation on the epidemiology of salmonellosis, basically on European conditions, but you will see that globally it follows with the same trends, and also speak a bit on monitoring, especially also of course on controlling salmonella. So first of all, we all know what salmonella is, of course, and it's a zoonotic agent, although that's not completely true. In many regions in the world, we also have both specific Salmonella serotypes and Calinarium, Salmonella tuberorum, which is causing quite some septicemia and severe disease in poultry. But these serotypes are not zoonotic. So today I will mainly speak about these Salmonella serotypes that have implications for human health. So these ones that can be transmitted from animals to humans by consumption of contaminated food products. So, as you know, well, there are quite a lot of Salmonella serotypes that exist, even more than 2,500 different ones. And these serotypes, well, one specific serotype is different in some cell wall components, which is basically flagellate structures and lipopolysaccharide structures. That's the basis of serotyping. You have two important serotypes for human health. The most important being Salmonella enteritidis and Salmonella typhimurium. So if you cover these two serotypes, you in fact reduce human salmonellosis cases by about 75%. That's why, for example, in Europe, legislation is really focusing on these two specific serotypes. If you can get rid of these two serotypes, you will basically eliminate most of the human cases. So a little bit on the epidemiology. If you look into all the different zoonotic pathogens, you will see that Salmonella is the second most important one. Today already we spoke a bit about Campylobacter, which is the most important zoonotic pathogen for humans due to consumption of food products. Okay? So these are European data. This is published by the European Food Safety Authority. In fact, each year we have a publication mentioning numbers of human food poisoning cases and outbreaks. What you can see here is that Campylobacter is number one, about 120,000 cases all over Europe. Some has a second variant for 50,000 cases. This is slightly different than, for example, 10 years ago, in which Salmonella was number 1. Basically, the reason why salmonellosis is currently number 2 is just because implementation of national European control programs in the European Union, which actually reduce numbers of human cases. So these are numbers of human cases, and if you look at it, Campylobacter and Salmonella, these are basically a lot of these human food poisoning cases are derived from consumption of poultry products. Okay? So poultry products are very important in transmission of foodborne pathogens to humans. Just some additional numbers, not that important, but this is what, for example, in 2021, so 2 years ago, was reported in Europe. A little bit over 50,000 cases, also some foodborne outbreaks, so 700 outbreaks, meaning that this is, for example, because people in a large group contaminate contaminated dish. Nursing homes, big conferences, so just one outbreak means that a lot of people get infected. We also see some deaths, 60, well, more or less 64 deaths annually over the European Union, which is not that much, of course, if you compare it to a lot of other diseases, also viral infections. We have corona, for example, so it's still quite limited. But of course, it's quite important because consumers do not want to get ill from consumption of food, including poultry. What you also can see here is that in the case of outbreaks, eggs and egg products are the most important food vehicle. So salmonella infections are mostly caused by consumption of undercooked or raw egg products. Okay? Desserts, for example, and all of other dishes in which undercooked eggs are being used. So eggs are the main vehicle for salmonellosis infections. If you look at serotype distribution, this is again human food poisoning cases in the European Union. You see that Salmonella enteritis, so the serotype enteritis, actually accounts for about 50% of human cases. Then you have typhimurium, which is causing 20 to 25% of human cases. And then you have a variety of other serotypes which are causing the rest of human cases. So basically, again, just saying that if you target enteritis typhimurium, you get rid of 75% of human cases. That's why, for example, European legislation, the focus is really on enteritis typhimurium. That's why vaccine companies develop vaccines that are based on enteritis typhimurium. Okay, so this is the reason why this is happening. Again, if you look at the food products involved in human cases, you see again that eggs and egg products and also dairy products are about 50%. This is really coming from some enteritis, which is specifically associated with eggs and egg products. A lot of other products, mostly meat, poultry, and mixed meat products, could be cattle, could be poultry, etc. So this is, for example, mixed meat products. Now, this is in fact a global situation. This is just a graph showing you that independent of the place all over the world, whether it's South America, whether it's the US, Europe, also countries in Eastern Asia, it's enteritis and typhimurium, these two serotypes, they really account for most of the food poisoning cases. So it's not really specific to Europe. I have no idea which serotypes are dominant here, but this is something global. Apart from maybe Australia, you can see that everywhere in the world, if you look at human data for salmonella food poisoning cases, it's really these two serotypes that are dominating. Okay, so it's quite important when we start talking about controlling the infection later on in this talk. And maybe something novel, the last 10 to 15 years, we see that there's one specific serotype that's highly emerging, and this is Salmonella infantis, specifically associated with broilers and broiler meat. So for example, if you look at all the meat samples that have been investigated for presence serotype. This has been rising since about 15 years. This is, of course, also quite important. This is something new. A specific novel serotype, in fact, novel clonal populations of certain serotype carrying specific fillers genes that are highly emerging everywhere in the world. These are European data, but in fact it's a bit everywhere. Also South America and Asia report this rising incidence of salmonella infantis. This does not mean that salmonella infantis is so important for human food poisoning cases, because of course if you think about consumption of poultry meat, this is basically always cooked or baked, of course killing off this specific pathogen. But just can be important in the future because salmonella infantis is also quite highly antimicrobial resistant. Okay? So this is of course also important for treatment of human infections. So this is a novel serotype coming up. I just want to show you these data here to explain a bit what happened in Europe. So what you see here again, it's numbers of human cases, and these are human cases reported in Belgium, so my country. If you would look at United Kingdom, France, many other countries, you would see more or less exactly the same, even in the United States. Okay? So what you see here is that the end of the 80s, suddenly salmonella enteritis emerged highly in the human food poisoning cases. So this suddenly came up. This is the green line here. So these are numbers of salmonella enteritis cases. At a certain moment in Europe, there was some European directive saying that it was obliged to start vaccinating breeders, breeder flocks, parent flocks, also focusing really on implementation of control measures to breeders. What happened is that even focusing solely on breeder flocks and also eradicating some enteritis contaminated breeders didn't really help in reducing these numbers of human cases. You can see that here. So at this moment, we started implementing a lot of measures in breeder flocks, and the incidence kept on rising. So that just says that only focusing on preventing vertical transmission from breeders to layers or broilers doesn't really help, so we need much more. And as already explained by you today, horizontal transmission is important, so that just means that if you only focus on breeding flocks and reduce vertical transmission, that will not help reducing human infections. So also this horizontal transmission is important. So you also need to focus on laying egg flocks or broilers, especially of course also biosecurity. But that just says that we need to really focus on the whole production chain, not only breeders but also broilers and layers. After implementation of measures to reduce salmonellosis in layers and broilers, this curve actually went down to very low levels. Okay? So implementing, controlling, monitoring and control programs in layers and broilers actually helped quite a lot in reducing human infections by salmonella enteritis. That's what you can see here. So there's a very steep reduction in numbers of human cases, and this was, for example, after the implementation of obligatory vaccination for layers. Okay? So at this point in Europe, there was an obligatory vaccination of laying hens, which actually resulted in a massive reduction in salmonella positive deaths. Okay? And as a consequence, also a strong reduction in human food poisoning cases by salmonella enteritis. The red line is salmonella typhimurium. You see a gradual decrease also because of vaccination programs, but salmonella typhimurium is a bit of a serotype that's not only coming from poultry, also from cattle products, from milk, from porcine meat, etc. So it's much more dominant also in other animal species and other meat type products from other animal species apart from poultry. So a little bit of an explanation of pathogenesis, because when we start talking about controlling salmonella, of course, we need to know how this pathogen is actually behaving. Okay? And if you think about salmonella infected, it's a pathogen that is not causing disease in chickens. Okay? It's an asymptomatic infection. If you have salmonella contaminated flock, broilers, breeders, layers, these animals develop no symptoms, they just carry the pathogen in the intestinal tract. Okay? So it's asymptomatic carriage, just the bacterium present in the intestinal tract without inducing any type of inflammation or any type of disease or lesions. Okay? That's of course quite problematic, but that means that older farmers of course do not really see when the animals are infected, and that's why you need this monitoring programs, this very intensive sampling. In fact, this is just a general overview of the pathogenesis. In fact, it's of course a pathogen that is taken up orally, by feed, drinking water, from the environment, whatever. It ends up in the intestinal tract, and it always colonizes the cecum. Okay? So if you really want to find salmonella in infected chicken, you have to take these two ceca. This is the place where salmonella is residing in an infected animal. It's an invasive bacterium, meaning that it is able to invade epithelial cells of the intestinal tract. Okay? And this is a very important process. When salmonella bacteria cannot invade epithelial cells, they never colonize. Okay? Why do I mention this? Because you have some compounds that reduce invasiveness and therefore also reduce colonization. One of the best examples is butyric acid, which is quite a lot used as bacterial additive. It blocks or it inhibits the process of bacterial cell invasion, causing a reduced colonization of the intestinal tract. So that's why this short-chain fatty acid is very important in reducing cecal colonization. The bacteria are in fact translocated to the bloodstream. They can survive within immune cells, such as macrophages. They go into the bloodstream and then they can end up in any tissue or organ of the chicken, spleen, liver, heart, but also especially the reproductive tract. This is of course very important for contamination of eggs. Okay? Salmonella is a bacterium, and especially Salmonella enteritidis is a bacterium that is very much capable of colonizing the oviduct and the ovaries. That means that is a route of internal egg contamination, so you have the possibility there that forming eggs are actually contaminated by this pathogen internally. This is what I will show in a few minutes. Maybe something just really important for monitoring is that if you have intestinal colonization, so cecal colonization, this bacterium is shed intermittently. That means that for monitoring purposes, if you start taking fecal samples using overshoots or other methods, that sometimes in infected flock you will find salmonella, sometimes you will not find it. Okay? It means that if you have an infected flock and you sample each week again and again, you will sometimes have a positive sample, sometimes a negative sample. So you can go up and down. That's what we call intermittent shedding. So it's asymptomatic carriage, and sometimes these bacteria are shed and sometimes not, which of course complicates quite a lot salmonella detection and monitoring programs. That's what I just mentioned. It can colonize the reproductive tract. Now what actually happens is that this is a picture of the oviduct of the chicken. There you have the ovaries. The yolks are taken up in the upper part, which is called equilibrium. So this is the oviduct of the animal. Here, this is the place where the egg white is produced. Then the forming egg is going down. You have the shell membranes and of course the shell around. That's how an egg is formed. If you look at the place where mostly you can find salmonella bacteria, is in this blue segment here, in which the egg white is produced. Basically, that means that the bacteria are present in egg white secreting cells. Okay? The bacteria are produced, are incorporated into forming eggs. So the animal is producing an egg that is contaminated internally. There's no change in smell, in taste, in color, nothing. The bacteria are present in quite low numbers in this egg white because egg white is antibacterial. Egg white can kill off any bacterium apart from Salmonella enteritis, which is very much capable to survive in this antimicrobial egg white environment. Okay? It's not proliferating, it's not doubling, it's just surviving an egg white, which means that the animal is producing an egg, internally contaminated, and of course if we start using it and eating it raw, undercooked, under maybe improper storage, okay, we can get contaminated with high numbers of these bacteria. This is a specific trait for Salmonella enteritis, okay? Other serotypes don't have this capacity. It's really enteritis that is having this characteristic. And that's of course why we have this global pandemic of Salmonella enteritis, because it hides itself into forming eggs and is present internally. Also, external contamination is possible just by environmental contamination where the eggs are laid. It can also be present on the external shell. But the most important reason for this Salmonella enteritis pandemic is the internal egg contamination. Okay? Now, monitoring. What I first wanted to do is just give a little bit of an update on European monitoring programs, but actually you can just download it free from the internet. European Food Safety Authorities published this whole list of monitoring schemes and programs that are used in breeders, layers, broilers, hatcheries, etc. So I decided not to do that. Basically what we do on farms is using overshoots, okay? Taking mixed fecal material and then trying to detect Salmonella. If you do that, it's clearly an underestimation of the real Salmonella prevalence, okay? Because the sample you take is quite limited, and if you start sampling very decently, you will be able to find much more Salmonella on the farms. We did some studies, also together with people sitting here, in which we took samples from Zika, from the animals, of flocks that were officially negative. So just when taking mixed fecal material, the flocks considered to be negative by official authorities. If you take Zika from animals, or euthanize animals who take Zika, you will see that about 20% of the negative flocks actually turned out to be positive. Okay? So the way in which, for example, in Europe, Salmonella monitoring is done is actually giving you a very strong representation. So we have many more Salmonella positives than are actually shown in the official monitoring reports. It's also quite important. But maybe the first point is tracking and tracing. It's quite logical, I think, what I'm going to say here. I just want to show you that if you find Salmonella wherever, in an egg, in meat, on a farm, it's always important to try to trace back where it comes from. Is it coming from the feed? Is it coming from the breeders? Just to try to track the source. Okay? And this is, of course, why you need to serotype Salmonella. So if you isolate it, you have to try to determine the serotype, maybe also to do some genetic fingerprinting. Otherwise, it's very difficult to trace back the origin. Now, this is just an example in which, for example, if you have a sample somewhere found to be positive, you need to have an ID number of that sample, and you need to try for any sample you isolate, you analyze, you have to try to give numbers so that you can actually know exactly, for example, if you have contaminated meat sample, that you can trace back from which slaughterhouse it is coming, from which farm it is coming, from which hatchery it is coming, from which breed it is coming, etc. That you can really try to trace back the infection to its origin. That of course needs quite some extensive sampling, but especially also let's say these ID numbers, these unique numbers of all the samples, so that you can trace back all over the production chain. So it's very important to record that very thoroughly. That's, for example, what we do in eggs and meat. In meat, for example, just on using the barcodes, which gives you an identifies the origin of that specific meat sample. Same for the eggs, which have also the country of origin, the producer number, the farm, the barn number, so the house number, etc. Just to be able to, if you find some positive eggs, to be able to trace it back to the farm, and not only the layer farm, but also the maybe the farm, etc. So that's a quite important first step. And of course, well, if you start monitoring for salmonella, as I just mentioned, in Europe, in the official monitoring programs, we basically use for the primary production samples, we use overshoots. Okay? As I just mentioned, this gives you quite some under-representation. If you really want to know whether a flock is negative or positive, you actually have to take much more samples than officially required. Okay? That's the only way to really get rid of salmonella farm, because otherwise you will have salmonella negative farms or supposedly negative farms that actually turn out to be positive in the next round. So it's much better to, if possible, to sometimes retake much more samples. Take larger samples as required, keep all the data, of course, and definitely also type the strains, ideally using some genetic fingerprinting methods, also here to be able to track the infection back to its origin. Okay? If you know the source of the infection, you really start thinking about how to implement control measures. Is it coming from feed producers? Is it coming from hatchery? Is it just horizontal transmission, etc.? This is what you will learn if you do that sampling problem. Also, some very important point is that if you take samples of salmonella, it's never present in all samples. For example, if you would have some positive broiler flock, that would in practice mean that maybe 5% of the broilers is positive. Okay? Meaning that also numbers of samples to be taken is important. That's why, of course, we take mixed fecal material. Let's take the same in any matrix you sample. If you sample hatchery flock, if you sample transport boxes, etc., you will always have this uneven distribution. Okay? So what you cannot do is just take 5 samples, because the chance that you will find salmonella is almost zero. You need to try to sample much more if you really want to know whether your flock is positive or not. And well, that's the only way to be able to trace back the infection to its origin and try to develop decent control programs. Well, I'm not going to focus too much on this in detail. I guess this is what I mentioned here is just some of the samples on equipment or type of samples that should be or could be taken in the, for example, hatcheries, chicken houses, feed mills, and after processing. There's quite much more that needs to be taken than what is just quite an official monitoring program, especially in Europe. We have this specific legislation that says how many samples that should be taken, but this is of course much more. What you see, for example, here in the hatcheries, if you take samples from the box liners, transport boxes, washing machines, hatchers, that at least gives you an idea, if you find salmonella, which parts you have to be much more careful, for example, cleaning and disinfection. So it really gives you some more info on the origin of the infection, and also, of course, by controlling the infection, it gives you much more information. So just not only try to take the limited low number of samples that's actually required, but sometimes take much more samples that are actually needed. Well, as I said, I'm not going to focus too much on this. On farms, well, as already mentioned today in the talk on biosecurity, it's impossible to get a farm completely clean or sterile. Try to focus on places that are visibly dirty and also take these samples. So just be a little bit creative, beware the sample if you really want to know that this farm is completely negative. Otherwise, it's quite clear, I think. In European legislation, it's always at least 25 grams that should be taken. But of course, you can better take more to enhance the chance of finding some positive samples, or to be really sure that your flock is salmonella negative. Okay? So this is also quite relevant. SIGA are the most sensitive sample type, as I mentioned in the few slides slides on pathogenesis. This bacterium is really colonizing Zika, so if you take fecal samples, this is the most sensitive, and this gives you the highest chance to find salmonella if present. If you take a lot of fecal samples that are all negative, you can be quite convinced that the flock is negative, and this is very relevant as well. Different ways here, just see a swab, you can actually just also take, of course, sequence droppings and enrich them in blood media, so possible. If you take samples, as already mentioned, try to take these samples that are visibly dirty. You see some feeding troughs here. You can always find quite a lot of places in forms where you find a lot of dust, organic material, cracks on the floor, whatever, feeding troughs, drinking water, places, etc. Often you can find it, even after cleaning and disinfection, quite dirty. For example, using these sponges that you can also enrich for salmonella, so this is a good way to find salmonella if it will be present. So this is just an example, or this is in fact an example of poor cleaning and disinfection, of course. This is not the way to go, but if you sample these places, it's quite often the places where you find these bacteria. You can find salmonella often back in the dust. Okay? If you have dust on the walls, on the roofs, on equipment, this is a place where also quite a lot of salmonella is quite often present if the flock is, of course, salmonella positive. As I mentioned, overshoots, this is what we use in official monitoring programs. We take 5 pairs of overshoots which we enrich for salmonella, so this is the way our official monitoring programs are about doing it. And of course, what I mentioned here is just an example. For example, for a brother house, this is just a sampling plan that could be potentially used. Okay? This is not the official way of sampling, but just an example. If you really want to do a thorough monitoring, if you really want to make sure that the flock is negative or positive, this is an example. You see that, for example, cracks, air inlet, feeding ponds, cables, and well, even also insects, of course. Etc. Feeding inlet, floors, ventilators, and so on. So you can just read here. On the right side here you see the frequency. For example, feeding pans, sponges, twice 4 sponges left and right side of the barn, etc. So this is quite a high number of samples. In official monitoring you take much less samples, but if you really want to be sure that you focus on negative, this is an example of what you could do. It needs quite some extensive monitoring. But if all these samples are negative, you can actually be very sure that your flock is negative. If you can find some other positive samples, anyway, at that moment you know exactly what is the origin and what type of equipment or space you need to disinfect much better. So this is giving you just an example for water, so you can say exercise for layers, video sections, etc. Again, some examples. Typically, places where you can find salmonella, if present, are dusty material, also your air inlet spaces, cracks, crevices, even ventilation shafts, etc. Also inlet of feed. So everything where dust can be present, this is a nice way if you really want to find salmonella. You often find it at these places, even after cleaning disinfection sometimes. Just a few final slides on monitoring. I was also, well, I get a lot of questions on feed. Can feed be salmonella positive? And it's definitely the case. Many different feed ingredients can contain salmonella, also soy, for example. Also currently still using meat and bone meal, animal products, byproducts that can often be salmonella positive. And in fact, as well, we would already mention today that feed should be treated in such a way that salmonella is eliminated, for example, by pelleting, by heat treatment. Even then, the final product can still be salmonella positive because you can have recontamination with dust from the feed mill. Okay, just the company producing the feed that can still either treat the feed, but then afterwards it can still be salmonella positive due to contamination with dust. But this is, of course, a difficult problem. It's not very easy. You should do heat treatment, but often you see that the final product, although less salmonella positive, can still be positive because of recontamination. places in the production lines. Also at the farm itself, which silos can be positive. It's also very difficult to eliminate, of course, once a silo or equipment that passes the feed from the silo to the farm is positive. It's very difficult to clean and disinfect. It's quite evident. But it's just an example of dust. You see that at different places. Palletizers, coolers, settling that dust can quite easily isolate some of these places when these feed samples are being positive. Final part on prevention and control, which is of course a very important aspect here, and it's already mentioned that biosecurity is very important. No vaccine, no feed additive, nothing works when biosecurity is not optimal. You don't even have to start vaccinating when you don't have decent biosecurity. That's very important to mention. I sometimes see some integrators of farms vaccinating, but when all biosecurity rules are neglected, it doesn't make any sense to start vaccinating. Okay, so it's really a multi-hurdle plan that you have to make. You need to keep your biosecurity under control, and then you can start doing other things such as vaccination for breeders and layers, which is very it's a very efficient strategy to reduce, for example, egg contamination. Dietary additives, some at least, to reduce colonization of the intestinal tract. And here I'm talking about probiotics, short-chain fatty acids, prebiotics, essential oils, whatever kind of dietary additive that is on the market as a feed additive for products or layers. So basically what I show here is the different targets. First of all, you need to reduce entry on the farm, which is, I'm not going to explain that, you did, so biosecurity is crucial. Reduce gut colonization by dietary additives or even vaccines. They also reduce gut colonization. Reduce systemic spread and especially reproductive tract colonization. Okay? And thus also egg contamination, and that's basically here the focus is on salmonella enteritis because it's the main single diet that is contaminating eggs, also typhimurium to some extent. And of course there are also slaughterhouse hygiene, that's evident of course, and of course also consumer education, how to use food products in the kitchen, that's of course also quite relevant. It's really of different targets. This is just one slide, but you will talk for 1 hour about it. I just want to show here that, that if you take measures, biosecurity measures should focus on the whole total reproduction chain, meaning from feed mill to slaughterhouse, egg packing plant, or even retail at consumer level, of course also the primary production level. I'm not going to focus on this slide because about biosecurity we talked quite a lot before. I just want to focus a bit more on vaccines, and dietary additives. Because we have quite a lot of experience in Europe using both live and inactivated vaccines, and they are quite efficient in reducing salmonella colonization. What I show here are indirect evidence data. This is a graph showing you in 2005 when obligatory vaccination programs were starting in Europe, that a study in which over 2,200 farms were sampled for salmonella detection, that in vaccinated farms about 5% was positive, and non-vaccinated farms about 30 to 40%. As I mentioned, it's indirect evidence, because you can imagine that flocks of farms that are vaccinating maybe also have better biosecurity, you don't know. But anyway, it's indirect evidence showing that vaccination is helping in reducing reductions in fetal contamination. Secondly, that's what I already mentioned, when obligatory laying-hen vaccination was done in Europe, you see this very massive reduction in human food poisoning cases by enteritis. So that's also indirect evidence. And here you see another graph. This is the salmonella flock positivity. The blue line here is 2005. The orange bars in 2014. You see quite huge reductions from about 20 to 60% of for positivity to levels close to 2 to 5%, which is actually a huge reduction over 10 years after implementation of obligatory vaccination programs in layers. Well, that's what I mentioned. 2020 is exactly the same. We also have these very low peaks. This gives you at least a hint on what monitoring and control programs can do. It's based on mixed fecal material, so this is the percentage of positive flocks in all these different European countries. Actually, the main reason of this reduction is improved biosecurity, but also obligatory vaccination in the layers. We have different types of vaccines, inactivated vaccines and live vaccines, and they both have merit, so they both can be used, either or not in combination. Okay. You see here, well, some differences. In fact, inactivated vaccines mainly are used to induce antibody titers, so systemic antibodies. Live vaccines have some additional advantages. One of them is, of course, that it can be used using drinking water applications, so easy in application. And it also is well, shown to induce not only antibody production, but also cell-mediated immunity, and also some mucosal immunity, so immunity in the intestinal tract by IgA, so immunoglobulins, antibody production in the intestinal tract itself. So there's some additional benefits. What is quite often done in real life is either triple dose live vaccination or double dose live once inactivated or only inactivated. It depends a bit on the management. In breeders, quite often it's inactivated vaccines, and there's combinations of live and inactivated. It depends a bit on the strategy of the farm that is using the vaccination. I'm just going to show you some experimental data that really show you that if you apply vaccines and then challenge the animals with allergenic salmonellosis rates, that you have a very strong efficacy. What I show here is a triple dose vaccination, 3 times live vaccine, a challenge with Salmonella enteritis at week 24, so 8 weeks after the final vaccination, and sampling 3 weeks later. Just showing you that if you look at systemic colonization and look at ovary and oviduct, this is a Salmonella enteritis vaccine. Salmonella enteritis vaccinated population, Salmonella typhimurium vaccinated population, Salmonella enteritis and typhimurium vaccinated population. This is a control population. You see that numbers or percentages of positive ovary and oviduct samples are actually reduced quite a lot. And you also see that percentage of positive eggs are reduced quite a lot with the 3 different vaccine preparations. Okay, just showing you that numbers of positive eggs, numbers of positive reproductive egg samples are reduced quite a lot when you just apply live vaccines and challenge the animals with quite high levels. So this is 10 to the 7th, so it's 10 million bacteria that were given to each individual animal. You can imagine that in field cases in which the infection pressure is much less, you probably have even a much better type of protection. Not going to focus too much on this, but this is cecal colonization, so intestinal colonization. Vaccination with a live vaccine at day 1 and week 6. 1 week after the second vaccination, Salmonella enteritis challenge, 10 to the 9, so a huge infection dose, and now 1 week later, sampling. This is intestinal colonization. Now what you see here is each dot, or each triangle, is the value for one animal. In the vertical axis is a logarithmic scale. What you see is that in the non-vaccinated group, you have some animals with very low salmonella numbers. That's inherent to this type of studies. Some animals seem to be less responsive. Immunity probably that develops somehow. But you see quite some animals with very high titers, so 10 to the 6 to 10 to the 8 bacteria per gram of cecal content, which is huge. Vaccinated group, all the animals have very low infection levels. Okay, so vaccination is really also resulting in quite a high reduction in intestinal colonization. Similar type of study, it's effect study that resembles a bit the previous slide. Triple dose vaccination, again an infection at week 27, organ sampling at week 27, challenge at week 24, and this is the percentage of positive batches of eggs. One batch is 5 eggs together in liquid broth. You also see a very strong reduction of egg contamination from about 75% to about 20% 1 week post-infection. So again, showing that enteritis and egg contamination is quite low when you start vaccinating. So yeah, we move now. Okay, remove my slides. Maybe one other aspect, a question we often get is whether if you vaccinate, for example, some enteritis or typhoid vaccines, whether this also cross-protects against other serotypes, which is very important in the last few years because we have this salmonellosis pandemic. What you see here again, live vaccine, it's an enteritis typhoid vaccine. Live vaccine, second shot at week 6, and here you have an infection with both. On the one hand, salmonella enteritis, on the other hand, salmonella infantis, 2 different groups, also sampling 1 week later. And you also see that while if you do an infection with salmonella infantis, you have quite a high number of animals with very high colonization levels. Okay. When you have vaccinated these animals with enteritis or typhoid live vaccines, you see that you have quite a lot of animals with values of salmonella infantis close to 0. On the right side is the data for enteritis. I have shown this already. But just saying that even if you would use an enteritis vaccine, it will cross-protect against a variety of other serotypes, which is of course quite important also if you think about breeder-end vaccination, for example, and reduction of salmonella infantis positive product flows. So you have quite some possibilities there. Pointer is not working for the moment, sorry. Okay, yeah. So on the next slide, you present further, yes. Okay, you can even push one down further. Another aspect of live vaccines is that even after the first vaccination shot with a live vaccine, the animals are highly protected against strains of the same serotype. So what you see here is a study which we vaccinated at day 1 and already gave an infection at day 2 to 5,000 salmonella enteritis bacteria, taking samples a few days later, and you see actually the same. This is an example of a protective mechanism that you do not have with inactivated vaccines. So you have quite an immediate protection against a challenge infection that is given 1 day after live vaccine administration. You see that here, very high colonization levels in the control group. After application of a live enteritis vaccine, you see that numbers of animals that contain high infection levels in the Zika, they are none, and they all contain very low infection levels. So live vaccines also protect immediate post first vaccination doses against strains of the same serotype. This is probably the most important example of a benefit of live vaccines as compared to inactivated vaccines. With which I do not want to say that inactivated vaccines are not useful, because they are very useful. They also can protect quite well. This is just an example of a study that was performed with inactivated vaccines, giving 2 doses, week 12, week 16, challenging the animals with salmonella enteritis, and then just collecting eggs and also looking at cereal content. And you have also quite a good result here with inactivated vaccines. Okay, you see that you have here in the non-vaccinated animals, quite some animals with high colonization levels in the Zika, while the animals in the vaccinated group have very low egg contamination levels. So both live vaccines and inactivated vaccines have benefits and merit, and we see that in the field quite often. People start using combinations. A final part in the last 5 to 10 minutes is about dietary additives. Because of course in broilers but also layers, and also previous even, quite a lot of dietary additives can be used to reduce some colonization levels. Maybe one important aspect is that that vaccines and dietary additives, they will likely never reduce salmonella levels in contaminated flocks to zero, but they help to reduce it to very low levels, acceptable levels. And then, of course, with the proper biosecurity, after a few rounds, you will be able to get to zero. And if you have a high infection pressure, they will never reduce it to zero. One of the most important dietary additives or drinking water additives are short-chain fatty acids, widely used everywhere in the world. This is acetic acid, propionic acid, butyric acid, even formic acid. Either as drinking water acidifiers to reduce contamination levels in drinking water lines, but also as dietary feed additives. This is present in many different forms. If you look at the market, you see that you have quite a different number of types of short-chain fatty acids containing dietary additives, esterified products, coated or encapsulated products, etc. If you think about drinking water additives, it's mostly acetate or formic acid. If you think about dietary additives, it's quite often butyric acid, which is quite efficient because it reduces single salmonella colonization levels, so it's quite an efficient molecule. That's what you see here. I'm not going to explain too much in detail, but this is just the result of an infection study in which the animals were challenged at day 5, salmonella enteritidis, these are broilers, and then samples were taken 3 days later in animals that were given a 1% dietary additive, coated product, formic acid, acetic acid, propionic acid, butyric acid, this is the control group. And you see that, especially butyric acid, coated products are quite efficient in reducing single salmonella colonization levels to about 2 logarithmic units, so about a 100-fold reduction in salmonella colonization levels. So this is what butyric acid is doing. The reason is that butyrate, I'm not going to focus on these graphs here, that butyrate is reducing invasiveness in epithelial cells. That's why this bacteria colonize much less. Just some data here, just infection trial data. This is a control population, powder form butyrate, coated butyrate, and a combination of powder and coated form butyrate. Animals infected at day 5 with 1 million salmonella bacteria, sampling done at day 8. And this is the colonization level, meaning that if you have 20 animals that you have infected, the control group, you see that 10 animals have very high colonization levels, about more than 10 to the 6th. No negative animals. If you use this coated product, you see that the numbers of very low colonized animals are very high. Just showing that this butyrate is quite an efficient molecule to reduce colonization levels. This is the percentage of birds that are shedding salmonella in feces. Butyrate coated feed additive control animals are given a diet without dietary additive. And I can give you quite a lot of more data on this. This is exactly the same as the previous slide, it's just a different study in which on the vertical axis the percentage of animals is shown with a certain infection level, as mentioned here. Again, this is a group of animals without dietary additive. This is a fat-protected butyrate, this is a wax-protected butyrate. What you see is if you infect the animals at day 17 and you take samples 4 days later, that the percentage of animals with very low colonization levels is rising quite high when you give the animals the butyrate coated additive. Never going to zero, but actually helping in reducing single colonization. Just 2 or 3 slides ago, prebiotics, quite often used also as a dietary additive, especially in broilers. What you see here is a study in which xylo-oligosaccharides are used. Xylo-oligosaccharides is a prebiotic substance, basically produced by the action of xylanases, so enzymes that we use in product diets to digest non-starch polysaccharides, or xylanes. And if you look on the top here, this is an in vitro experiment. We have different test tubes. You have just cecal droppings, you not in the test tube, and then you have these different substrates, okay? Fructooligosaccharides, siderooligosaccharides, inulin, starches, cellulose, different test tubes. If you incubate that and you measure butyric acid production in vitro, you see that these three substrates are actually converted heavily to butyrate, starches, cellulose, or mud. If you then do an infection trial with one of these three substrates, you will see that addition of these substrates as a prebiotic is reducing salmonella colonization. And the reason is also here that these substances are converted to butyrate in the intestinal tract of the animals. And that's what you see here. Day 14 challenge infection, and then sampling Zika at different time points post-infection, 3, 7, 11. And you see that at each time point, 0.4% of inclusion as a dietary additive of salmonellosis is giving you a multiple logarithmic unit reduction, so 100 to 1000-fold reduction in Zika colonization. You can do the same with fructooligosaccharides and inulin. If you do that with cellulose starch, it will not work because it's not converted to butyrate. Just some final slides. Well, probiotics is the question I often get as well. In fact, most of the probiotics that are used in poultry, they have an effect in the small intestinal tract, not in Zika. So therefore, there's often not a very consistent effect on salmonella colonization levels. That's why I just mentioned this here. If you have a question on probiotics, ask the suppliers to give you some good data, because most of the probiotics are poultry or bacilli strains, and they mostly colonize the small intestine. It's not the salmonella is colonizing. So it is also quite important. So just the final slide, sorry. I mentioned that enteritidis and typhimurium are the main serotypes to control, because basically they cause 75% of all the infections. Enteritidis mostly by laying hens and egg contamination. Typhimurium by contamination of different types of meat. Can be cattle meat, but also broiler meat for sure. Biosecurity is an essential component. Without decent biosecurity, it doesn't make any sense to use anything else as a control measure. But vaccination is very efficient, especially to reduce colonization of the intestinal tract and reproductive tract in laying hens and breeders. It's a very efficient method on top of biosecurity that will really eliminate most of the human infections, because you have very strong reductions in positive egg samples. But also specific dietary additives can be quite useful. I mentioned butyric acid, we also have some others that can also be added on top of this vaccine and biosecurity story. So it's really a multiple step approach in which multiple components should be used in these control programs. And of course you have monitoring to really figure out whether any of these strategies you are using are beneficial or not, or have effects. This was my final slide. Thank you.
Any questions for? Yes.
Thank you for such an important and very useful presentation. My question is, since eggs and protein or the quality are going to be processed, at what temperature can you tell the salmonella itself? Will the egg, since it's going to be boiled or fried or eaten itself?
So normally, if you go up to over around 58, 56, 58 degrees for a few minutes, it's definitely killed. So you can kill them quite easily by heat treatment. The most important problem is, in fact, that especially for eggs, sometimes they are still not baked or cooked efficiently. That's the most important problem because it's quite easy to kill these bacteria. With meat, it's a bit different. It's basically the handling of the meat in the kitchen that is the problem. For example, if you have meat, put it on the kitchen, take it off, then you put some raw vegetables on it, and you start consuming these. So it's, in fact, consumer handling of meat and eggs is crucial. If you would learn consumers how to handle the meat and eggs properly, that should eliminate the problem. But apparently this is definitely not what is happening in real life. But you're right, it's 50-60 degrees more or less to get the temperature for dry sun.
What's the symptoms that can occur of having an infection of the body?
Symptoms?
Symptoms for
humans. Yeah, for humans, well, in fact, symptoms are very mild. In general, symptoms are mostly seen in young children, elderly people, immunocompromised people. So the infection itself is not too severe. Symptoms are basically just gastrointestinal symptoms: vomiting, nausea, diarrhea. One day, a few hours, 2 days, that's it. It's only in very sensitive people that you can have much more severe disease. So basically, the main issue is, of course, that especially in Europe, that consumers don't like infections caused by food that is contaminated. The symptoms are generally mild. And healthy individuals, it's self-limiting, a few hours of diarrhea, and that's it. So mostly even not treated. Yeah.
So it's not epidemic.
Sorry?
It doesn't cause death.
Well, there are about 60 deaths in Europe annually caused by salmonella, but 60 deaths is, in fact, if you think about many other reasons of mortality, it's very, very limited. So that's definitely true. Yeah.
Any more questions?
Thank you very much about this presentation. It was very clear, but I would like to ask you about your opinion about salmonella phage, which is a virus. Salmonella phage, which is virus, was sprayed on the carcass or given in the water for poultry. So this, hopefully you state, talk that this product minimized the salmonella because this virus is attacked this salmonella and killed it and minimize the population of salmonella in the carcass, also in the intestine. What's your opinion about this?
No.
Is it clear for you?
Well, phages, we're not allowed to use that in Europe. In the US, for example, it's done. Also in India, I know some companies that sell phage cocktails of salmonella. The only potential problem with phages is that they are quite specific for certain types of salmonella. So that's why you have different phage types. So if you use phages, you would need like a cocktail of phages that target different salmonella phage types. That's the only disadvantage, of course. If you do that on carcasses, I think it can be worthwhile doing it. In the gut, it will be probably much more difficult. But on carcasses, you can imagine if you isolate strains and you pick the correct phages that can help reducing contamination out of smaller carcasses. I can imagine that this happens. There are some companies that develop phages based on the isolation of the strains. So they isolate strains from carcasses and then they test phages and they look at which mice best to target that specific strain, and then they start using it as soon as possible.
Can you consider this way is a promised way in the future?
I think it can be, yes, if you start using either cocktails or you isolate a strain, you the process should be very rapid, of course. Otherwise, the difficulty is that you almost have to know what type of salmonellosis, trace, serotypes, fish types are present before you can apply. But I think it's promising. If you find features that have a much broader host specificity, it would be worthwhile testing it, definitely. I don't have experience with it myself, but I saw some data from companies that actually show quite good results. That's another question.
Thank you for the fruitful presentation about salmonella, and you have mentioned reducing salmonella prevalence and colonization in the gut of the chicken using butyrate. I have read also literature regarding using calcium butyrate. One Netherlands company have produced a new product with calcium butyrate using as a control measure for salmonella colonization in the gut. But if we talk about the butyrate will not, as an acidifier, will not be tolerated by the proventriculus pH. As you know, the proventriculus is the glandular part, and the pH is from 2 to 4 in chicken.
No.
So, can you comment on this point, that the acidity of the butyric acid will not be tolerated by the chicken organ itself, and what are the preventive mechanisms I can use as Netherlands trying to make a method in order to stop this tolerance?
Yeah, we have been testing a lot of different butyrate additives, like a dozen, and the only ones that we found to be highly efficient are the ones that are, let's say, releasing the butyrate quite distal in the intestinal tract. When you have early release, you don't see any benefit. When you have quite a release in the intestinal tract, it goes quite well. So when you have increases in, let's say, distal ileum, cecum, butyrate concentrations, it's quite efficient. So there's some coated products do that. If you have coated or just single butyrates without any coating or encapsulation or acidification, then you don't see a lot of benefits. So it's really related to the only butyrate additives that we see that are efficient or the ones that are releasing the butyrate really further down in the intestine. So yeah, so there's a lot of variability. One type of product, you have a dozen of different types, different formulations, concentrations, coatings, whatever. So you always have to look at the data for that, because you have the same in probiotics, but if hundreds of bacilli activated in the market, some work, others don't work, because the colonize is less efficient, etc., etc. The same with butyrates. But you have to look at the release location.
Okay, thank you.
Okay, thank you very much for the session. We have
we have a 10 minutes quick break for the Asr prayer. After that, we will be proceeding with Dr. Inu Velayudan.